Hello, everyone. Welcome to the last session on Saturday of ICCP. I hope you're enjoying the conference. This session 2C, has many wonderful imaging strategies that we're going to go into right now. Before we start, I just want to remind all of you to please participate on the live chat and ask questions. You can start while the video is playing, so we have time to answer all the questions when the authors come on. So let's start right now with our first paper, which is called Modeling Defocus-Disparity in Dual Pixel Sensors by Abhijit Punapurat, Abdullah Abulaim, Mahmoud Afifi, and Michael S. Brown, all of them from York University. So let's look at the video right now.
Good morning. This is the presentation for paper ID 21, Modeling Defocus Disparity in Dual Pixel Sensors. I'm Abhijit Punapurat, and this is joint work with Abdullah Abu Alaim, Mahmoud Afifi, and Michael Brown. Here is the outline of my talk. I will begin with some preliminaries on how the design of a dual pixel sensor or a DP sensor differs from a conventional sensor. We will examine what the DP sensor was originally designed for and why they exist on almost all modern DSLR and smartphone cameras. A few recent works have proposed to use the data from the DP sensors for tasks beyond what they were originally designed for. We will look at what these applications are. DP sensors produce two subaperture views of the scene from a single image capture, and there exists a disparity between these two subaperture views. Here, I'm showing you a simple animation that is switching between the two DP views. We will analyze the model of disparity that existing DP sensor-based methods adopt and what the shortcomings are of this model. Having covered these preliminaries, I will introduce our model of DP defocus disparity using the image formation model on a DP sensor. Next, we will identify a key symmetry property of DP defocus kernels and introduce a parametric version of this DP defocus blur kernel, which we will then apply to the task of depth estimation. One main advantage of our method is that we can exploit the symmetry property of DP kernels to construct an unsupervised loss function that does not require ground truth depth. We will also demonstrate how a CNN can be trained for faster inference. Finally, we will validate our method's effectiveness with experiments on both DSLR as well as smartphone DP data. Most modern DSLR and smartphone cameras use DP sensors. Unlike in a conventional sensor, where each pixel site has one photodiode, on a DP sensor, each pixel site is split in half using two photodiodes. These two photodiodes can collect and record light independently. When the two signals are summed, the intensity you get is what you would observe on a normal sensor, and in fact, this is what the camera outputs as the image pixel intensity. However, analyzing the two signals independently yields some very useful information. It allows the camera to perform fast autofocus. Let us say we want to focus on the foreground object on the left. The autofocus routine on the camera analyzes the local disparity that exists between the two DP views and determines how to move the camera lens in order to bring that particular region of the scene in focus. A few recent works have used the information contained in these two DP subaperture views to solve other computer vision tasks beyond autofocus, such as synthetic bokeh, depth estimation, reflection removal, etc. These existing methods view the two DP subaperture views as a stereo pair and use stereo matching algorithms to compute disparity. The image shows a typical stereo camera configuration. Here is a simpler depiction of how the two cameras are positioned in a stereo setup. Notice that there is a physical baseline separating the two cameras, and the disparity observed is the result of view parallax. If you think of it as a virtual camera at the center being shifted left and right, then at any given pixel, the stereo model for disparity can be represented using two shifted impulse kernels. That is, Classic stereo treats disparity as an explicit shift in image content between the two images. We have covered the preliminaries. The question we are trying to address is whether the stereo model of disparity used by current methods holds for the DP scenario. Let us take a close look at the image formation model on a DP camera to find out. For simplicity, let us analyze the case of an ideal DP camera first. Consider a scene point that is at the focal plane of the lens, that is, an in-focus scene point. Light rays emanating from this point travel through the camera lens and are focused at a single pixel. There is no disparity, and the blur kernel is an impulse in the left and right DP views as well as the image. Notice that the left half pixels integrate light over the right half of the aperture and vice versa. Now consider a scene point that is behind the focal plane. Light rays emanating from this scene point converge in front of the sensor and produce a 7-pixel wide blur on the sensor. The circle of confusion that is induced by this out of focus scene point is split over the two DP views, producing half circle blur kernels as shown. The sum of these two blur kernels is equal to the full circle of confusion observed on the image, since together they account for all the light passing through the aperture. In a similar manner, rays from a scene point in front of the focal plane also induce half-circle blur kernels. While the combined kernel corresponding to the image is exactly the same as earlier, the kernels corresponding to the left and right DP views have swapped positions, making it possible to disambiguate whether the scene point is behind or in front of the focal plane. And the disparity is proportional to the signed blur circle radius. Also notice an interesting symmetry property of the kernels corresponding to the left and right DP views. The left kernel equals the right kernel flipped about the vertical axis and vice versa. The half-circle kernels correspond to an ideal sensor and lens. To investigate how the shape of the kernels deviate from the ideal case, we performed experiments on real data captured using DP cameras. We estimated independently the kernel corresponding to the image as well as the left and right DP views. These are shown in the bottom row. As expected, the shape deviates from the ideal half circles and the falloff is gradual. But what is interesting is that the kernel symmetry property still holds to a fair extent even on real DP data. This can be visually observed from the figure and is also verified quantitatively from the normalized 2D cross-correlation values which are close to unity. Let us examine the image formation mathematically. Consider a constant depth patch in the scene as shown by the zoomed in region. The left DP patch GL is the convolution of the underlying sharp patch F with the left DP kernel HL. Note that F is usually unknown. Likewise, the right DP patch GR is F convolved with the right DP kernel HR. The combined image G is the sum of the left and right DP views. Alternately, G can be expressed as F convolved with the summation of the left and right DP kernels HL and HR. The combined kernel H is the sum of HL and HR. To summarize this section, the disparity observed between the left and right DP views is the result of blurring by these two opposite blur kernels and is not due to an explicit shift in image content as in classical stereo. We have seen that DP disparity is due to defocus blur, and furthermore, the left and right kernels have an inherent symmetry property. In this work, we are targeting the problem of depth estimation from DP data. Consider this relationship between the left and right DP patches and their associated blur kernels. Please see our paper for the derivation. Using our kernel symmetry property from earlier, we can express this relation in terms of a single unknown kernel HR, and our loss function can now formally be expressed as the loss function states that the left DP patch blurred with the right DP kernel equals the right DP patch blurred with the flipped right DP kernel. The non-negativity and sum to half constraints are because HR is a blur kernel that integrates light over one half of the aperture. The recent DP depth estimation paper proposed both an unsupervised loss based on classic stereo matching, as well as a supervised loss which was shown to be more accurate. However, the supervised loss required ground truth depth which had to be computed by building a custom-made rig of cameras, carefully synchronizing capture, and applying classic multi-view stereo algorithms. In contrast, our loss function is unsupervised and does not require ground truth depth. We further parameterize the DP kernel as a translating disk such that the signed radius S of the disk is the only unknown. This helps to further simplify our optimization, and our final cost function takes this form. Our kernel symmetry assumption, based on which our cost function is constructed, holds only for a constant depth region of the scene. To obtain the depth map given a test image, we apply a sliding window approach. Instead of solving an optimization problem for each window, we can instead train a CNN so that inference is faster. Please see our paper for more details. Let us now look at some experimental results on DSLR and smartphone DP data. These are results on the Canon DSLR camera. The deep learning based monocular depth estimation methods fail to distinguish the foreground objects in most cases. The unsupervised stereo technique fares better in comparison, but produces erroneous depth estimates, particularly in the first two examples. In comparison, both our optimization-based and CNN-based approaches produce more accurate depth maps. Here are some more results captured outdoor or in more unconstrained settings. For quantitative results, please refer to our paper. Here we show some comparisons on data captured using the Google Pixel 4 smartphone. In general, we found that pixel data is more challenging, particularly for faraway scenes. This is mainly because smartphone data has higher levels of noise compared to the DSLR, and the disparity is lower due to the smaller aperture size. However, as can be seen from our results, our methods still produce fairly good depth estimates. To conclude, we examined the image formation on DP sensors and proposed a parametric blur kernel to model DP defocus disparity. We selected the task of depth estimation and demonstrated the effectiveness of our PSF formulation of DP disparity. Thank you. I'll be happy to take questions during the live Q&A session.
What a really wonderful paper showing an interesting connection between defocus and disparity. So as before, please put on your questions in the live chat, which I can select. Abhijit, I have a few questions for you while we now the first question, suppose you're doing this kind of depth estimation on an edge, sort of on an edge, and there's something behind the defocus kernel and in front. How does your work in this situation?
Yes, so the assumption is that our cost function assumes that we are looking at a constant depth region of the scene. So on a depth edge, this assumption, this kernel symmetry assumption will be violated. So, but as I explained in the video, we are doing a sliding window based approach at test time, given a test image. And so, although I didn't go into details in the video, we do make our noisy depth map edge aware at a later stage with some post-processing using some bilateral space techniques. So yeah, you're absolutely right. At a depth edge, because this assumption is broken, there will be some noisy disparity estimates.
All right, thank you. So we have a question from George Chen. He says, great work. For smartphone DP sensor, since the aperture is very small and the sensor is very small, the depth of field is very wide, i.e. everything is in focus. Does the model still work in general? That's his question.
Yeah, that's a very good question. So most of our results are on DSLR, and there you have a bigger fat aperture, and we have shown results. But we also showed some results on the Pixel 4 smartphone. So In general, we found that smartphone data is much more challenging than the DSLR, exactly for the reasons that you mentioned, that because the aperture is much smaller, beyond say like 2 meters or so, almost everything will be anyway in focus. So this works only for nearby scenes with, I mean, if there are depth variations and it's a nearby scene. That is true. Also, on mobile phones, there is more noise, and even the lens distortions were a little higher than in the case of the DSLR. So, in general, yes, we found mobile phone data to be much more challenging, but we were still able to get reasonably good depth estimates for the examples that we tried.
All right. So we have more questions. So Shankaranan says, very nice work and results. I'm curious if is the kind of defocus model can be further enhanced using coded apertures. That is there a potential to get the right and left defocus blur more different? That's the question.
Yeah, that's not something we have looked at, but it's definitely an interesting question. I think, yeah, that could be possible. I mean, you might be able to get further, I mean, you may be able to get a better disparity if you try some coded aperture tricks, for sure. Yeah.
All
That's
right.
not something that we have tried in this work, though. Yeah.
All right. So we are actually running out of time, but there are a bunch more questions. So please go ahead and answer them online and in the session break coming up. But right now, we'll head to the next paper. The next paper is Wished, a Wavefront imaging sensor with high resolution and depth ranging by Yicheng Wu from Rice University, Fengquang Li from Northwestern, Florian Willomitzer from Northwestern, Ashok Veeraraghavan from Rice University, and Oliver Cossart from Northwestern University. And it'll be presented by Feng Qing and Yi Cheng. And let's go ahead and look at that video right now.
In this video, we introduce our paper titled Wished, Wavefront Imaging Sensor with High Resolution and Depth Ranging. This is a joint work from Rice and Northwestern University. When a 3D object is illuminated, the reflected optical field contains two components. The amplitude part contains the albedo information of the object, while the phase is related to the depth map. For current CCD and CMOS sensors, they can only record the amplitude, while the phase information is lost. To measure the phase information, there are currently three types of sensors. First, we can use continuous wave time-of-flight sensor based on amplitude modulation. The principle is to use an RF signal to control the amplitude of the laser diode. At the same time, another same RF signal is sent to the camera as a reference. The camera compares the phase delay between the reflection and the reference signal to estimate the depth. The modulation frequency for time-of-flight camera is usually tens of megahertz. With such modulation frequency, we have limited depth resolution to centimeters. Optical interferometry can also be treated as a time-of-flight camera. The detector compares the phase delay between the reference beam and the sample beam to estimate the depth. The modulation frequency is optical frequency, which is more than 100 terahertz. With this frequency, we can achieve extremely high depth resolution. Due to the need of the reference beam to estimate the phase, the system is bulky and sensitive to vibrations. On the other hand, wavefront sensors do not need a reference beam. Traditional wavefront sensors are based on geometric optics. Schacht-Hartmann wavefront sensor is the most frequently used design, which builds an array of lenses in front of a CMOS sensor. But the spatial resolution of the measured complex field is very low. Recently, computational imaging-based wavefront sensors have been introduced with high spatial resolution. The key idea is to combine optical modulation with computational algorithms. Although wavefront sensors can provide extremely high depth resolution, these sensors cannot be used for microscopic objects. It is because the unambiguous depth range, which is just hundreds of nanometers, is much smaller compared with the object height variation. For optically smooth surface, phase unwrapping algorithms may help alleviate this issue, but typically fail for objects with discontinuity. While for optically rough surface, it results in speckle patterns with random phase. In this paper, we introduce a wavefront imaging sensor with high resolution and depth ranging, named WISHT, which enables depth ranging on macroscopic and rough objects. In our proposed WISHT system, there are two key components. We use a tunable laser to illuminate the object sequentially with two close wavelengths. For each wavelength, we adopt a computational imaging-based wavefront sensor to estimate the optical field with high spatial resolution. By using the tunable laser, we exploit the wavelength diversity which has been used in optical interferometry. During the imaging, we measure two wavefronts using two different wavelengths, λ1 and λ2. When we combine these two wavefronts coherently, we get the beat frequency, which provides a synthetic wavelength as shown below. We choose the λ1 and λ2 to be very close to get a large synthetic wavelength. For example, if we use two wavelengths with 0.03 nanometer difference, we can get a synthetic wavelength of 24.4 millimeter. The unique measurement range is increased by more than 10,000 times. In this way, we are able to measure objects with large height variations. To recover the wavefront for each wavelength, we adopt a computational imaging-based wavefront sensor which consists of a spatial light modulator and a CMOS sensor. Since the phase SLAM is in reflective mode, the beam splitter is inserted. Multiple uncorrelated random phase patterns are displayed on the SLAM to modify the incident wavefront. The corresponding intensity images are captured by the sensor. Then, the Gauss-Berg-Sexton algorithm is applied to iteratively update the field on the SLAM and the sensor plane. After several iterations, both amplitude and phase is recovered. Since the surface of the simulated bunny is rough, speckle pattern and the random phase is observed. Similarly, we recover the phase for the other wavelengths. The depth can be estimated by pointwise multiplication between the field of the λ1 and the conjugate field of λ2. The estimated depth map is shown on the right. RMSE is only 85 micron compared with the 24.4 mm synthetic wavelengths.
Based on this principle, we built up an experimental prototype with a tunable laser as a light source. The center wavelength of the laser is 850 nanometer. The beam from transmissive or opaque objects goes through a linear polarizer. The signal is then directed into the wavefront sensor through a lens. For the wavefront sensor, we use a phase modulator and a CCD camera. We tested our prototype on objects with different materials. First, we verified the best performance of the prototype by imaging a transparent object. The light will pass through the 4 letters, and we add one extra plate between 2 adjacent letters. The thickness of each glass plate is 1 mm, and it brings an optical path difference, OPD, of 0.5 mm. We show the intensity from the sensor readout and the phase map with an optical wavelength. As we can see, the phase map is wrapped with the single wavelength. On the other hand, we can resolve the phase map with the synthetic wavelengths. We use the phase map with large synthetic wavelengths as a guidance to unwrap the phase with smaller synthetic wavelengths. We can convert phase estimations to OPD using corresponding synthetic wavelengths. We plot a line profile of the depth map. As we can see, smaller synthetic wavelengths marked with the blue dots can provide better depth resolution. We further quantify the RMSE between the measurement and the fitted ground truth, which provides the same conclusion. The best performance with our prototype is 9 micrometer. Then we measure a translucent object whose surface is not optically smooth. We put a diffuser on the top surface of the glass stack to set up the object. The thickness of each glass plate is 1 millimeter. Spicules are observed in the intensity. Since we use two close wavelengths, the spicle patterns are very similar. If we reconstruct the phase with the single wavelength measurement, the phase of the reconstruction is random. It is hard to estimate depth information from this measurement. We can estimate depth information with the synthetic wavelengths. We plot a line profile across the depth map and quantify the performance compared to a fitted ground truth. With this object, we can get an RMSE of 69 micrometer. Lastly, we tested our prototype on a real-life opaque object, one center coin. The thickness of the letters compared to the background on the coin is about several hundred microns. Since the surface is rough, spicules are observed in the intensity. Again, it will fail to measure the phase with a single optical wavelength. With our method, the surface head of the coin is reconstructed using a synthetic wavelength of 2.63 millimeter. We also measure the coin with superheterodyne time of flight. Superheterodyne time of flight is based on multiple wavelengths interferometry to get a macron depth resolution. However, superheterodyne time of flight provides a very limited lateral resolution with the lock-in sensor compared to our method. In current prototype, we use a cubic beam splitter between the phase modulator and the sensor, which limits the field of view. We can replace the modulator with a transmissive modulator to increase the field of view. Moreover, current sensor is not suitable for moving objects. That is due to multiple measurements in acquisition and iterative reconstruction algorithms. In the future, we would like to reduce the number of measurements and use a faster reconstruction algorithm, such as deep learning-based method. To summarize, we offer a novel depth sensor. It provides a micron depth resolution up to 9 micrometer and a high lateral resolution. We tested our prototype on transparent, translucent, and opaque objects. Thank you for your time and attention.
Well, that was an extremely interesting paper on very, very fine reconstructions. And so right now, you can put your questions and we will ask them. Yicheng, the first question is from Benjamin Attal. He says, in your experimental setup, do you solve for the wavefronts due to each individual wavelength independently or jointly?
So in our current case, we're doing this separately. So we will first optimize for the wavelength 1 and then the wavelength 2 and then combine them together.
All right. Then the next question we have is from Wei Yu Chen. Is the laser a perfect delta function in spectrum? If not, how wide is the laser spectrum band?
So the laser is not a pulse laser. It's like a continuous wave laser. So I guess the question is like how accurate the
So I'm going to interpret. I don't know, but I think
Sure.
the question is about coherency. How far, if you make it partially coherent or things like this, how can you get your system to work?
Okay, I think for our current system, it's actually the laser is actually quite coherent. So which means that it gives you a very large this coherent distance.
All right. Then the next question is by Chinmay Telegonkar. It says, great talk. Can a learning-based method be used for the phase retrieval step also?
Yeah, that's a very interesting direction we want to do, actually. So right now we use the GS algorithm. So it's actually quite robust and give you very high accurate resolution, but the trade-off is that it's very slow. So if we can somehow use some learning-based method, especially we can put some prior knowledge of the object, and we can using these. And another direction is actually we can use like unroll algorithm, right? Because we know how the phase retrieval algorithms looks like. We can unroll this iterative method to be like a network kind of based, and it might help us to speed up the reconstruction process.
All right. We just have a little bit of time, so I have a follow-up question on that, on the issue of speed up. How fast does the, actually we have another question, so let's just ask the audience.
Sure.
How well does it work for objects that exhibit subsurface scattering and multiple bound slide paths, so sort of interreflections, multipath?
Yeah, that's actually, we will not tackle that problem yet. So what we observe is that based on our current principle, it won't work for very deep like subsurface scattering effect, because what we assume is that we assume depth is directly related to the phase. So that's a key assumption here. So if they're very heavy scattering effect, then this assumption won't hold.
All right. Well, we're out of time, and there are going to be more questions there. So please ask the authors questions. I think it's time now to go to the next paper. So the next paper is Distance Surface for Event-Based Optical Flow. It's by Mohammad Al-Matrafi, Raymond Baldwin, Kiyoharu Aizawa, and Keigo Hirakawa. They're all from the University of Dayton, the University of Tokyo, and the Al-Qura University. So Mohammed is going to be presenting, and let's now go to the video.
Hello, my name is Mohammad Matrafi. Before I get started, I would like to wish everyone a good health. It's my pleasure today to be presenting our distance surface optical flow paper here at ICCP 2020. This work is funded in part by Ford University Research Program. For our overview, I will give a quick introduction to dynamic vision sensor, or DFS, for those who are not familiar with it. Then I will present our new method to take data from DFS to improve state-of-the-art for optical flow. Dynamic vision sensor, or DFS, is completely different from active pixel sensor, or APS, which is what you see in ordinary cameras. APS reports frames at fixed frame rate, while DFS asynchronously reports spikes, called events, when the log intensity changes exceed a fixed threshold at each pixel. The figure on the left here shows an example of DFS output versus APS output for a single pixel. As we can see, events are only generated when there is a change in log intensity, and each reported event contains the exact timestamp at which it occurs, the spatial location, and the polarity, either 1 or -1, corresponding to whether the change was positive or negative. On the animation on the right, events are sampled at 10 milliseconds and overlaid on frames to visualize the principle. Moreover, we can see that events are very sparse, and that enables the DFS to have high temporal resolution of over than 800 kHz, high dynamic range of more than 120 dB, low data rate, and low power. DFS with these characteristics have the potential to improve the optical flow performance that's currently limited by the low frame rate of APS. Optical flow is known as the estimation of the apparent motion in the scene, and here is the well-known optical flow equation, where Ix and Iy are the spatial derivatives that are usually computed from the first frame. It is the temporal derivative that's usually computed from a difference of 2 frames. U and V are the motion field that I would like to estimate. Ix and Iy here has the best fidelity in APS. It, on the other hand, has the best fidelity in DFS. So our previous method in attempt to improve optical flow performance combines both ABS and DFS by estimating IX and IY from ABS and IT from DFS. It has a state-of-art performance, but the limitations are the dynamic range and the frame rate. If we take away the ABS, then we have to come up with a way to estimate the IX and the IY. Recall that DFS lack the spatial information, and therefore the traditional optical flow method that are usually applied to frames cannot be directly applied to the sparse event. So prior efforts have attempted to overcome this issue by generating a proxy to image intensity to enable the adaptation of traditional optical flow methods. Here is an example of such a proxy where events are accumulated over a short temporal window, and as we can see that the accumulated events have poor spatial fidelity, which affect the estimation of the spatial derivatives Ix and Iy that can lead to unreliable optic flow. While these methods overcome the dynamic range and the frame rate issues, the performance is sacrificed. So we need a way to estimate the spatial derivatives, so we need a better proxy for image intensity. Here we show some of the state-of-art methods. First, we have the locus and canade DFS-based method, which first generates a proxy to ABS frame using the accumulation of event approach, then adapts classical locus and canade optical flow method. Second, we have the FlowNet method, which is a learning-based method that trains a network to predict the motion based on events. Third, we have the ABS plus DFS, which is our previous algorithm, which combines both ABS and DFS to estimate the spatial derivatives and temporal derivatives respectively, and then adapts optical flow methods. Our goal is to get excellent optical flow performance that's similar to the state-of-art performance of the ABS plus DFS method, but without the dynamic range and the frame rate limitations. This means that we need to come up with a better proxy, and therefore we propose here to use the distance transform as a proxy for object textures. We assume that we have rigid-bodied object and all edge pixels have similar edge velocities. For distance transform, we use the L2 norm distance metric. In this toy example, the solid colors indicate the edge pixels. The number are the distance value, where the color of the numbers indicates the corresponding closest edge pixel. As you can see here, the distance transform values are computed from many edge pixels of different orientation, which helps improve the quality of optical flow estimation. Here on the left, we show an example of our proposed distance surfaces on real data. We show animation that contains a sequence of edge maps shown in yellow dots overlaid on the corresponding distance surfaces. Events here are sampled at 1 millisecond to generate the edge map, and the playback is at 100 frames per second. Here we show the distance transform optical flow equation, and in our paper we have shown that the optical flow equation that's used to be an approximation in frames is exact in distance transform. That means no approximation by Taylor series expansion is required, and so the quality of the optical flow would be improved as a result. Here we show an example of the input parameters to the distance transform optical flow equation. Given an edge map, we compute the distance surface, which is then used to compute the spatial derivatives in x and y direction. The temporal derivative here is estimated from the difference of two distance surfaces. Now we would like to talk about the robustness of distance transform, and here we show an example of distance transform where we only show L1 norm rather than L2 to make it easy to follow. Black pixels represent edge pixels, and the distance transform is known to be robust to jagged edges as well as missing events, but it's sensitive to falsely occurring events as shown by the blue pixels. Due to the fact that DFS injects considerably high noise, distance transform will benefit from a denoising step. In our paper, we have presented our denoising algorithm in details, and we have shown that our denoising algorithm improves the performance of all DFS optical flow methods, including ours. And here we show an example of our denoising algorithm, which filters out the red dots corresponding to noise and keeping the other dots corresponding to valid events. We summarize our distance surface optical flow algorithm with these schematics. First, detected events are passed through our denoising to clean up the events. Then we apply temporal window to generate the edge maps, which are then passed through distance transform to create the distance surfaces. Distance surfaces are then passed through the traditional optical flow methods to estimate the motion field. In particular, we use the classical Horn-Schunck algorithm with Lorentzian penalty function. For evaluation, we introduced a new optical flow dataset called DFS Motion 20, collected using DFS hardware sensor. The dataset contains both indoor and outdoor scenes, fast and complex motion, and moving camera and moving objects. The moving camera sequences here have a ground truth recovered from IMU. These last two sequences contain multiple objects moving in opposite direction. Here we show optical flow results on the camera motion data. Each row represents a sample of a different sequence, and each column gives the result of a different optical flow method. Motion is overlaid on frames only for visualization purposes. In the first column, we have the ground truth motion inferred from IMU. In the second column, we have the results of the ABS plus DFS method. And here we emphasize that this method uses ABS in addition to DFS, and therefore it does reliable across all scenes. The remaining columns have DFS-based optical flow methods that do not have access to ABS and only use DFS. Third column here shows the results of the locus uncanny DFS-based method. Notice here arrows look noisy and are spatially inconsistent. Fourth column gives the results of the learning DFS-based method. Notice here arrows pointing away from the vertical edges. This is a phenomenon called normal flow, which does not necessarily represent the true motion as with the case here. Last column shows the results of our proposed method, which as you can see are consistent and stable across all scenes, even though our proposed method does not have access to ABS and only uses DFS. In fact, our proposed method results closely resemble the ground truth and that of the ABS plus DFS method. Last row shows the special case where the motion is purely horizontal. And we can notice here the learning-based method does really well, and that might be because this sample is similar to the training data. Here we show the results on the multiple objects motion data. The trend is the same as before. In the second column, we have the locus uncanny DFS-based method, and you can notice especially here the orientation of the motion is not spatially consistent, and the arrows pointing everywhere. In the third column, we have the DFS learning-based method, and clearly here it has a problem with the motion magnitude, which is not consistent with the context of the motion. In contrast, here we have our proposed method. Despite the fact that our proposed method do not have access to the ABS, it does really well across both scenes, similar to the ABS and plus DFS method, and especially in handling the spatial variations in the scene, as well as reserving the motion boundaries. Here we show a short video containing the optical flow results of our proposed method versus the DFS learning-based method. On the left, we have our proposed method, while we have the DFS learning method on the right. As we can see that despite the fact that our proposed method does not have access to the ABS, it does provide consistent and stable results across multiple samples of different scenes. This can only show that distance transform is well suited to optical flow. We attribute this improvement to the exactness of the distance surface-based optical flow equation. For error statistics, we report the average angular error as well as the relative average endpoint error referring to motion angle and magnitude respectively. In our paper, we have shown that our denoising algorithm improves all DFS-based methods, including ours, and therefore we only report results with denoising. In both paragraphs, blue is the ABS plus DFS method, orange is the locus uncanny DFS-based method, gray is the learning-based method, yellow is our proposed method. And the overall trend says that ABS plus DFS method does better, and that's expected since it uses an extra information in ABS that's not available to other DFS-based methods. However, our proposed method outperforms all DFS-based methods by a large margin. And if you look closely in both paragraphs, you can see that our proposed method results are very comparable to that of the ABS plus DFS method. And there is in fact only 2 degrees separating the performance of the two algorithms. Finally, our proposed method outputs motion at much higher frame rate, at 1000 frames per second compared to 60 frames per second by the ABS plus DFS method. To summarize, we proposed the notion of distance surface that uses distance transform as a proxy for object texture. We showed that the motion recovered by our proposed method is highly accurate. We employ FN denoising to improve optical flow performance. We present a new optical flow dataset called DFS Motion 20 of complex scenes and camera motion. DFS Motion 20 dataset is available at issl.udayton.edu, and the codes will also be available soon. Thank you all for listening, and now I would be more than happy to answer any questions you may have.
A wonderful paper showing really nice closed form solutions for getting really high quality optical flow. As I asked before, please put your questions in the discussion chat. Mohammed, I have a few questions just to start off.
Yes.
High level question. Your distance transforms really look a little bit like Voronoi diagrams. Did you have that kind of connection between Voronoi and Delaunay triangles? And do you have kind of this dual in the transform space?
Can you repeat the question? Sorry, I didn't get it.
So your transform really looks like Voronoi diagrams. And connection between Voronoi diagrams and Delaunay triangles. Do you have this kind of inverse of your transform? Have you looked at the dual?
No. We haven't looked at that. We only use the L2 norm distance metric.
Okay. Excellent. So we have a question from Winston Wang. He says, thanks for the interesting talk. I'm wondering if the method has been tested when the APS images are significantly blurred.
So to answer this, first I need to emphasize that we do not actually use APS here. Our proposed method only uses the DFS, the offense, which like it shouldn't be like affected by the blur because it actually outputs the offense actually operate at more than 800 kilohertz, so it should actually be robust to fast motion.
All right. And then the another question that I had was about heavy occlusion. So if you're tracking hands behind some station or something like this, I know you showed some missing pixels in the diagram. Could you explain a little bit on your distance transform? Is it robust to heavy occlusions?
Well, what we showed like two sequences with like multiple cards moving in opposite direction, and we have two hands moving in opposite direction, like in actually the back offer a textured background, and we showed that actually our algorithm does really well, especially like reserving the motion boundaries there. So it showed to be robust to occlusion because like the DFS actually gives offense right at the occlusion region, and that actually helps our algorithm to actually handle the occlusion region and reserve the motion boundaries.
I see. Very cool. So I just have one last question before we go to the next talk. But so have you thought, I know you have a data set, are you looking at sort of learning from a conventional camera, RGB, now that you have almost ground truth, you have like really nice optical flow with your DVS? Are you thinking about inferring from a sensor which does not have the transform advantage?
Do you mean that should we use like a learning-based method?
Yes.
With the ground. So for us, actually, we were interested more of like the theoretical solutions, such as the exactness of the distance transform. Second, our method can be used actually as a pre-processing step for learning-based method. One popular approach in learning-based method actually compares the offense to some sort of surface, which can be then used in the CNN-based method. So our distance surface can be used as a pre-processing step to any learning-based method. But we haven't looked at that, but which is something, it's actually interesting, and we might actually look into that in the future.
Excellent. Well, thank you so much. And let's now move to the last talk in our session. This is a paper titled Fast Confocal Microscopy Imaging based on Deep Learning by Xiyu Li from Tsinghua University, Jiuyang Dong from Tsinghua University, Bowen Li from Tsinghua University, Yi Zhang also from Tsinghua, Yongbing Zhang from Tsinghua, Ashok Veeraghavan from Rice University, and Jiang Yang from Tsinghua. And it'll be presented by Ji Yang. And let's go on ahead now to see the video.
Topic is faster confocal microscopy imaging based on deep learning. The content of my speech includes the following parts: motivation, related work, proposed methods, datasets, results, limitations, and future work. As we all know, confocal microscope is one of the most popular and important tools in bioimaging due to its desirable ability to capture high-resolution three-dimensional images, even in the presence of tissue scattering. This is accomplished by the use of two confocal pinholes that simultaneously ensure that most of the scattered lights from background points are rejected. While the ability to reject scattered photons is powerful, this comes with an especially steep cost. To ensure this, point scanning is essential. This means that even to achieve a moderate spatial resolution of 1 micron over a field of 1 cubic millimeters, one needs to scan 100 million points, even with a short pixel dwell time of 1 microsecond. This would mean a total capture time in minutes, making imaging dynamic targets challenging. So how can we speed up the imaging process of confocal microscopy to ensure the high imaging quality under the strict constraints of low light throughput and short pixel dwell time? Confocal microscope usually uses a much more sensitive detector such as avalanche photodiode and performs point raster scan. In addition to the use of a highly sensitive detector, various methods have also been proposed to speed up the imaging process of confocal microscopes. Traditional methods employ a pair of galvanometric mirrors to steer the laser beam over the sample, but the imaging speed is far from satisfactory due to the inertia of the mechanics scanners. As shown in the slide, in addition to physical-based methods, model-based methods, especially CNN, are also worth trying. Recently, deep learning is emerging as the hotspot and the mainstream methods in many image processing applications due to its overwhelming performance compared to other algorithms. Since Dong et al. Proposed their pioneering work, SRCNN, which tries to construct a high-resolution image by learning nonlinear low-resolution to high-resolution mapping, implemented as a shallow conventional neural network. Deep learning-based single-image super-resolution methods have attracted extensive attention. As deep learning technology has received more and more attention from the academic community, some pioneering work combining deep learning and microscopy has achieved good results. Robustness et al. Blindly tested deep learning approaches using various tissue samples that are imaged with low resolution and wide field systems, where the network rapidly outputs an image with better resolution, matching the performance of higher numerical aperture lengths, also surpassing their limited field of view and depth of field. Wang et al. Tried to improve the resolution of wide-field images acquired with no numerical aperture objectives, matching the resolution that is acquired using high numerical aperture objectives by using a GAN framework. It also demonstrated cross-modality super-resolution, transforming confocal microscopy images to match the resolution acquired with a stimulated emission depletion microscope. The above two articles also use deep learning tools to improve the quality of microscopy imaging results, and in that sense, they are related to our work. There are several significant differences as well. Confocal microscopy by its nature targets imaging of highly scattering samples, and all of our results are of samples with significant scattering. Neither of the above two papers address tissue scattering at all. Second, we adapt machine learning algorithms to significantly tackle the primary practical challenge in confocal microscopy, the speed of acquisition, and show a diversity of results demonstrating significant improvements in speed of acquisition from a low-resolution input are acquired using the faster scanning mode or a conventional or elliptical disc confocal microscope. Even for a modest 4 times resolution difference, the capture speed can be 16 faster since the total number of sampled points has a square dependence on sampling resolution. Our technique for super resolution of confocal images is based on a generative adversary network, as shown in the slide. The network has two major components, a generator and a discriminator. We design a generator to synthesize an natural image by feeding a single AR image, and a discriminator D is devised to distinguish whether the image produced by the generator is real or fake. The generator pipeline consists of 3 components, namely filter extraction module, back projection feedback module, and the reconstruction module. We first extract features in the AR space employing filter extraction module. Then we design a back projection feedback module to map the features extracted from AR space to HR space, and then map the feature back to AR space iteratively. Finally, we reconstruct the super resolved image by upsampling the regression of the low-resolution features in a ratio structure. The feedback module is one of the most important structures in our proposed network design. The feedback architecture mainly provides 2 distinct advantages. First, using feedback connections makes it possible for networks to transmit response information to previous layers. Consequently, the reconstruction process can be effectively guided by this information backflow. Second, feedback or recurrent structures can essentially reduce network parameters without any degradation in reconstruction performance. Reduction in number of network parameters is key to making the learning problem feasible, given the capacity of data for training. To fully explore the benefits of the feedback scheme in the network architecture design, we devise an advantaged back projection feedback module to get a more powerful error to actual mapping with fewer parameters as shown in the slide. We use n projection groups in each iterative process and recurrent the architecture for t times in each training step, and correspondingly tie the loss of each loop together to be optimized. Besides using overall recurrent structure to learn a better mapping, we also try to find a better mapping in both downsample and upsample blocks to map error and actual images more successfully, especially in cases with a large scale factor. We also introduced the ratio structure into our upsample and downsample block. Parallel that, the loss function design in neural network training plays a critical role in the final performance. One typical example in the ESRG model, which employs the improved realistic adversary generative loss and enhanced perceptor loss to favor outputs residing on the main fold or natural images. With these two loss terms, ESRG model significantly improves the overall visual quality of reconstruction over Pearson-oriented methods. However, such a loss function will result in crosstalk effects, especially for microscopic images. The slide provides a visual comparison between the reconstructed results by such a loss function and ground truth in both spatial and Fourier frequency domain. We notice artifacts around the filament in the reconstructed result by the event conventional loss function as shown in image E. In addition, we also observe the artifacts in the Fourier frequency image as indicated by the yellow arrows in image H. Since the Fourier frequency domain has global information about the spatial image, the artifacts appearing in H will inevitably degrade the visual quality of the reconstructed image. The result in image E, the consistent artifacts in both the spatial and frequency domain reverse the principal shortcoming of the conventional loss function and also provide inspiration for our proposed Fourier transform loss. Motivated by this phenomenon, we propose a Fourier transform loss, as you can see in the slide. We use two hyperparameters both equal 1 to avoid the occurrence of gradient exploding problem. Images were obtained by image human normal breast epithelial resuscitation capture cells. MCF10A. The equation configuration is shown in table 1. We collected MCF10A1 dataset with 60 objective lens magnification and MCF10A2 dataset with 20 objective lens magnification. Each dataset contains images with 4 different sizes of 256, 512, 1024, and 2048. The pixel size is inversely proportional to the number of pixels per image, and it is also inversely proportional to the magnification of the objective lens. In the dataset MCF10A1, we totally collect 100 samples, where each sample has 3 channels, and each channel has 17 layers with 0.282 micron between adjacent layers. The 3 channels respectively excited by 488 nano, 561 nano, and 640 nano lasers. We selected 693 image pairs from the first channel as our 4 times super resolution data set. In the data set MCF10A2, a total of 23 samples are collected. Here, each sample has 3 channels, and each channel has 46 layers with 0.489 micron between adjacent layers. We selected 208 image pairs from the first channel as our 8 times super resolution dataset. As shown in table 2, we randomly divided the dataset according to the ratio of 8 to 1 to 1 to serve as the training, validating, and testing dataset respectively. We tested our 4 times super resolution model over MCF10A1 and the 8 times model over MCF10A2. For scale factors, we compare our BPGAN results with 3 state-of-the-art super resolution models, Pearson-oriented methods, DBPN and SRFBN, and the GAN-based method ESRGAN. We can find that our proposed BPGAN outperforms SRFBN and DBPN with more natural breast textures. A common disadvantage of these Pearson-oriented methods is that the recovered results are too smooth to see the details and the textures clearly. At the same time, a common disadvantage of GAN-based methods is that where they can obtain good visual effects, some textures and details that do not exist in the original images are generated, or unpleasant artifacts and mistakes. When compared with ESRGAN, it can avoid this phenomenon successfully. In the next 3 slides, we provide some other results compared with the 3 state-of-the-art models, and you can clearly see the difference. To test the robustness of our method, we give the generalization analysis in this and the next slide by testing the new data collected by the same MCF10A sample under different confocal microscope configurations. We mainly conducted two generalization experiments, namely feature size generalization, collecting samples whose size are different from training data while maintaining other configurations unchanged, and objective length generalization, using objectives with different magnifications to collect training and testing images respectively, while keeping other configurations unchanged. Due to the limited capacity of the dataset we collected, we only conducted generalization experiments on feature size and objective length. We will try to collect more different types of samples so that we can conduct sample generalization experiments.
What an interesting talk about speeding up confocal microscopy. We have Ji Yuang here to help us answer some questions about this. As before, please put your questions on the chat window. Yuang, just to start before we get some questions, I had a question about whether you all have thought about putting in the microscopy in the loop for your algorithm by outputting uncertainty. So if you are uncertain of where your reconstruction or super resolution is, that you could put more samples there in a sort of a guided upsampling kind of way. Have you thought about that at all?
Sorry, I didn't hear you very clear for my balance work. Can you speak again?
Yes, absolutely. So actually, before I do that, there's a question from the audience, and I'll get back to my question in a second. So George says, for the FFT loss, does it help high frequency texture more or low frequency texture more?
I think it helps. It is more helpful for texture more.
Okay.
Yeah.
I see. So texture is helpful. So back to my question. Have you thought about can you think about a change to your algorithm where you output the uncertainty in the image, the parts of it that you're not sure about? Do you have that kind of? Are you able to do that?
Yeah. We have sort of question, and I think we will take this as our one part of our future work.
All right. I also have a question about the hybrid loss. So have you done a proper study of your hybrid loss to see the two components, how much they contribute? Have you done an ablation study for that?
Yes. And you can see the
more important. Sorry, go ahead.
And you can see the hyperparameters for each part. We use the grid search to find which is more important for the overall reconstruction result.
All right, excellent. So we might have more questions on the chat. Remember, we have 1 more hour of we have some more time for asking the questions. So we're running out of time here. Before I go, there's a couple of announcements Ian wanted me to make. The first announcement is everyone who's registered for the conference will have got an email about voting for the best poster and demo. And I hope you please go ahead and answer that Survey Monkey so we can figure out the best poster or demo to give that award tomorrow. I also want to remind everyone to take selfies and upload them so that we can have the group photo, the synthesized group photo that we're doing. And then finally, we are starting again tomorrow at 10:30 St. Louis time. So I hope all of you will be there, and please continue to interact on the chat window. And thank you so much.